The last section of logarithms and exponents is called logarithmic scales. Our goal today is to use logarithms to model practice problems and become familiar with common log scales, such as pH, Richter, and decibel. So the Richter scale. I'd like you to take a moment, just pause, and read through this. The following formula for the Richter scale given in the Sullivan book measures the size of an earthquake in terms of the reading on a seismograph. The equivalent formula gives the same measurement in terms of the actual energy, E, in joules released by the earthquake. As it can be seen from the following example, this formulation allows us to compare the actual strength of two earthquakes. So for example, if magnitude equals 2/3 times the log of E, which is energy in joules, divided by 10 to the power of 4.4, then how much energy is released in a magnitude 7 earthquake? The following chart on the right gives you lots of information about earthquakes and just kind of gets you to have a better understanding of them. So if I want a magnitude 7 earthquake, well, I don't want one, pardon me. If there is a magnitude 7 earthquake, how much energy is actually released? Okay, so my magnitude is 7, and that will equal 2/3 times the log of E over 10 to the power of 4.4. Now, I have one log, so usually I write things exponentially, but I need to get rid of this coefficient first. So if I want to get rid of the divide by 3, I'll multiply both sides by 3. And if I want to get rid of multiplying by 2, I will divide by 2. So that leaves me with 21 over 2, or better yet, 10.5. 10.5 is equal to the log of E, so the amount of energy, over 10 to the power of 4.4. From there, I have an isolated log on one side, so I can write things exponentially. So I'll go 10 to the power of 10.5 is equal to the amount of energy divided by 10 to the power of 4.4. From there, to isolate E, I'm going to multiply both sides by 10 to the power of 4.4. And this is going to be a huge answer, so it's energy, and it's only in terms of joules. So instead of actually evaluating this and turning it into a number, I'm going to write it as a power of 10. So here I'm multiplying things with the same base, so I'm going to add their exponents, and I end up with E is equal to 10 to the power of 14.9 joules. If you do care to evaluate that on your calculator, it's going to be a huge, huge, huge number. Approximately 1 and 15 zeros. So I don't even know how many zeros I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that many joules. So a lot. And that's an approximation, of course. Hence why it's easier to write 10 to the power of 14.9. Okay, so this is one example of a log scale. However, a more typical question looks like the ones here. It says, how many times stronger, in terms of energy, is a magnitude 7 earthquake than one that measures 6? So how many times stronger is one than the other? Well, if I want to measure the intensity of, let's say, the first one in comparison to the second, the intensity of the first is going to equal this reference intensity, whatever that reference is, times 10 to the power of the magnitude, which is 7. The intensity of the second one is going to be equal to my reference intensity times 10 to the power of 6. Now, if I want to know how many times stronger this one is than this one, well, then I can just divide the two. So if I look and have my reference intensity times 10 to the power of 7 divided by reference intensity times 10 to the power of 6, my easiest simplification is to cancel out those reference intensities because they're going to be the same. Which leaves me with 10 to the power of 7 divided by 10 to the power of 6. Subtract your exponents and you're left with 10 to the power of 1, or 10 times. So on the Richter scale, every time something measures one level higher, it becomes 10 times stronger. So if we use a little bit of logic at number 2, how many times stronger is a magnitude 8 earthquake than one that measures 6? Well, if this one measures 6 and one measures 7 and it goes up by 10 times, if I want to go all the way up to 8, it's going to be another 10 times. Now 10 times 10 is 100 times. So every time it takes a step up that scale, it's going to increase tenfold. So the final answer will actually be 10 times. To show this in our equation, if this magnitude 8 earthquake is the first one and the magnitude 6 is the second, the intensity of the first is equal to the reference intensity times 10 to the power of 8 divided by, because it's how many times stronger it is, the second intensity, which equals your reference, times 10 to the power of 6. My reference intensities will cancel out, and hopefully you're starting to notice a pattern. That leaves me with 10 to the power of 8 over 10 to the power of 6. I have the same base, so I can subtract my exponents, and I have 10 squared, which equals 100. So here, I've proved it. Now, I've done 2 questions, which are very similar, and in both of them, I did the same first step. So it's almost like there's got to be an equation that simplifies this one up top. And there is. The intensity, when I'm comparing 2 earthquakes, can be shortened into the form 10 to the power of the stronger divided by 10 to the power of the weaker. And this is a shortcut formula. We're going to use 3 of them in this section and then summarize them at the end. Okay? So in this one, how many times stronger in terms of energy is a magnitude 6 earthquake than one that measures 6.9? So I have 10 to the power of the stronger, which is 6.8, 10 to the power of the weaker, which is 6. I know this isn't one full step apart, so I know it should be under 10 times. See though. So I subtract my exponents. 6.8 subtract 6 will give me 10 to the power of 0.8. Then I grab my calculator. 10 to the power of 0.8 will be approximately 6.3 times. So less than 10. So what I'm going to do right now is I'm going to take this equation and I'm going to copy it to the very back page. The very back page is empty, and here's my first shortcut formula. And this is for the Richter scale. Okay? There's one. Now we're going to go back, and our next topic is the decibel scale. So the decibel scale is used to measure the intensity of a sound or the power level of an electrical signal by comparing it with a given level on a logarithmic scale. On the right-hand side, there's a bunch of examples. Decibel 10 is a pin dropping, so it's super, super, super quiet. 20, rustling leaves, or a ticking watch. 3 is a whisper. As you can see, it's coming up here, and at approximately 85 or 90, one of those two, I can't remember, this is where we should actually wear hearing protection if we're going to hear something for a prolonged period of time. So think about if the garbage disposal was going consistently, it would be a lot. Or a lawnmower is going consistently, it becomes very, very loud. Okay, so anything over that level could potentially ruin your hearing. If you notice in comparison though to our Richter scale, in the Richter scale it's going up by ones. Here we're increasing in increments of 10. So similar to the previous example, we must use the formula in order to compare the intensity of 2 sounds. Let I represent the intensity of sound, and I naught represent the reference intensity, which is the quietest sound the human ear can hear. So here is my formula. Now, how many times louder is an 80 decibel sound than a 70 decibel sound? Okay, well here's my first intensity, or pardon me, there's my first loudness and there's my second one. So the intensity of the first is going to be that reference intensity times 10 to the power of 80 divided by 10 all over my second intensity, which is equal to my reference intensity times 10 to the power of 70 over 10. Now, similar to before, my reference intensity is consistent, so it cancels out. That leaves me with 10 to the power of 8 divided by 10 to the power of 7. Dividing things with the same base, so I can subtract their exponents, which leaves me with 10 to the power of 1, which is 10 times. So here, I have a very similar process that I went about, except for what's different. The thing that's different in this one is the divide by 10. Now I can remember to divide by 10 because deci means 10. So I can divide by 10. So in this question it says how many times louder is an 108 decibel sound than one that is 100? Well, if I compare the intensity of two things, I'm going to start with my shortcut formula here. The intensity is equal to 10 to the power of the louder divided by 10 all over 10 to the power of the quieter divided by 10. So my louder is going to be 10 to the power of 108 over 100, over 10, divided by 10 to the power of 100 divided by 10, or 10 to the power of 10.8 over 10 to the power of 10, subtract my exponents, and I have 10 to the power of 0.8, and 10 to the power of 0.8 is going to be that 6.3 times louder. So at this time, I'm going to take this shortcut formula and I'm going to copy it to my back page as well, because this is another formula that's going to come in handy a lot. So this is for my decibels. Now to go back, you can always use logic on these, and please let it help you. Every time it goes up 10 decibels, it becomes 10 times louder. So if let's say there was something that was 90, and you wanted to know how many times louder something is that was 120, well, you'd have to go up 1, 2, 3 steps, or 10 to the power of 3, which is 1,000. So please always use logic when you're doing these questions, and it can really reduce some of the options if it's multiple choice. And our last one here says, how loud is a noise which is 20 times louder than something which registers 72 decibels? Okay, so my intensity is equal to 10 to the power of the louder divided by 10 over 10 to the power of the quieter divided by 10. In this one, I have the intensity. It's 20 times louder. So 20 will equal 10 to the power of, well, I'm trying to figure out how loud is something that is louder. So my x will be in the numerator. And in the denominator, the decibel rating that I have is 72. Now, if it's 20 times louder, it's one full step up on the decibel scale, so it's at least 82, but it's not 2 steps up, because if it was 2 steps up, then it would be 100. So it's below, 2 steps above 72 would be 92, so it's got to be between 82 and 92. So I'm going to go about solving this. Subtract my exponents, so I have 20 is equal to 10 to the power of x minus 72 all over 10. exponents on one side, so I can write this logarithmically as log base 10 of 20, which equals my exponent. From there, times my 10 over to get 10 times the log of 20 equals x subtract 72, and then add my 72 over. And let's see what we get. Remember, should get an answer here between 82 and 92. So I have 7.2 plus 10 times the log of 20. And I get an answer. Oh, sorry, that's not 7.2, that's 72. I was like, whoa, that doesn't make sense at all. Let's try to see it. 72 plus 10 times the log of 20, which is 85. Okay, that makes sense. But hey, if I didn't think logically about this question, I would have just gotten my answer and been like, okay, sounds good, continuing on. So how loud is something that's 20 times louder than something registering 72 decibels? It'll be registering 85 decibels. The final log scale that we're going to look at is the pH scale. The pH scale measures how acidic or basic a substance is and ranges from 0 to 14. Take a read through the part on the left, so press pause, and then take a look at the chart on the right-hand side. As we notice in the chart on the right-hand side, the things that are the most acidic are actually at the bottom. The things that are the least acidic are at the top of the chart and have the largest pH. Also make note that the concentration of hydrogen ions compared to distilled water is very, very high when things are acidic. As we go down one step on our scale, things become 10 times more acidic. So if I want to know how many times more acidic a grapefruit is than tomato juice, well, it's got to be 10 times more acidic. So the formula for calculating pH is given in this form. So pH is equal to the negative log of H+. Well, where H+ is the concentration of hydrogen ions in a solution. A comparison of the acidities of two liquids is obtained from the ratios of the H+ concentration. So I have the H+ concentration of the more acidic divided by the hydrogen, or the amount of hydrogen ions in the less acidic substance. So that's my comparison, but if you notice in the formula that it gives, the amount or the concentration of hydrogen ions isn't isolated. So that's what we're going to have to do right away. So how can I isolate that? Well, the first thing I need to do is get rid of that negative coefficient. So then I have negative pH is equal to the log of H+. To isolate that, I have to write it exponentially, so 10 to the power of the negative pH will equal the concentration of hydrogen ions. So what is my shortcut formula going to look like here? Well, if I'm comparing the acidity of two things, I compare the concentration of hydrogen ions of the more acidic, which can be represented in this form, divided by 10 to the power of negative pH of the less acidic. So how is this going to look? If the question says how many times more acidic is a solution with a pH of 3 than a solution with a pH of 4.1, what I can do is I can say the intensity is equal to 10 to the power of the negative more acidic pH divided by 10 to the power of the negative less acidic pH. Which one's more acidic? Well, the pH of 3. So 10 to the power of negative 3 divided by 10 to the power of negative less acidic, which is 4.1. Still, like always, dividing things with the same base, so I subtract my exponents. Here I'm subtracting a negative, which will give me 10 to the power of 1.1. When I go to evaluate 10 to the power of 1.1, I should get a value of 12.6 times more acidic. So if you look at our shortcut formula here, it looks different once again. So if I compare the intensities of two things, I have 10 to the power of the negative more acidic divided by 10 to the power of the less acidic. And that's my last shortcut formula. So please make sure you have those three in the back page. So Richter scale, straightforward. Decibels, deci, divide by 10. And for my pH, I need to have a negative in front of my different pHs because our scale is essentially upside down. Okay, so two practice examples. How many times more acidic is a solution with a pH of 2.4 to a solution with a pH of 4.1? I have 10 to the power of the negative more acidic divided by 10 to the power of the negative less acidic will equal my intensity. So when I plug it in, I is equal to 10 to the power of negative 2.4 divided by 10 to the power of negative 4.1. If you notice, the difference between these is not, well, it's more than one full step. It's not quite two full steps, so it's got to be somewhere between 10 and 100. To simplify, I'm dividing things with the same base, so I can subtract their exponents. Subtracting a negative, so I'm going to start that again. I'm subtracting negative 4.1, or adding. So I have 10 to the power of 1.7. So how many times more acidic is something that is 2.4 in comparison to 4.1? It should be 50.1 times more acidic. And that does make sense. Should be between 10 and 100. And our very last question. A solution is 200 times more acidic than a solution with 5.4. What is the pH of that solution? I'm not sure if you noticed, but I write my formula every time. It is 200 times more acidic. Now a solution is 200 times more acidic, so I don't know how strong that one is, but I know the less acidic one is 5.4. Combine my exponents, and I have 200 is equal to 10 to the power of negative x plus 5.4. Now there's only an exponent on one side, so I'll write it logarithmically. So log base 10 of 200 will equal negative x plus 5.4. And I know it might be an extra step, but I'm going to add this x over because I want it to be positive. And then I'm going to subtract the log of 200. That leaves me with x is equal to 5.4. Subtract the log of 200, which is 3.1. If I do a little mental check, if I have 3.1 here, 4.1, 5.1, so this is times 10. This would be times 100. So is 5.2 about times 200? Yeah, that would make sense. So the pH of the more acidic substance will be 3.1. And that is the end of log scales.